Okay, I really haven't thought this problem through all the way, so this might take a while. But here's the basic idea. So you have a guy or girl, and they jump off this 10-meter platform, which is scary as it is. And during that fall, they start off with some initial angular rotation. I'll say it's this way. It's a back tuck. I'll call that omega 1. And then during the fall, they tuck. And when they tuck, they increase their angular velocity into omega 2. And so the question is, how many times can they do a flip before hitting the ground? And I don't know what the actual answer is for the record here. And I don't know. I'm going to make some approximation for some values here. So let's just get started. The first thing we want to think about is, well, if this person is falling and spinning, how many times they rotate depends on how long they fall. So the first thing to do is calculate delta t, how long it takes to fall. So I'm going to say I know that the acceleration in the y direction is negative g, negative 9.8 meters per second squared. So with that, I can call this y equals 0, and I'll call h my initial y. Then I can use the following kinematic equation. Y final equals y initial plus Vy initial t minus 1/2 gt squared. That's actually a delta t. Okay. And if the person starts from rest, that term is 0. If the person ends up down here at the ground, that term's 0. And that's h. So I get 0 equals h minus 1/2 gt squared. So if I add this term to both sides, I get 1/2 gt squared equals h. Now I'm going to solve for t, multiply both sides by 2, divided by g. T squared equals 2h over g. So t equals the square root of 2h over g. That's important. We're going to need that. Okay, so now we have the time. That square goes all the way down. I can get values for this, but I'm not going to right now. Okay, so I know h, I know g. Okay, next thing I want to do is I'm going to estimate this omega 1. If I jump off a platform, let's say I can rotate, my initial rotation is as a standing human stick. Let's say that's a 1 rotation per second. So 2 pi radians per second. I'm just totally estimating that. I mean, totally. Okay. And now I need to say, well, what's going to happen as this person falls down? The angular momentum of this person is going to be constant because there's no torque. So I could say angular momentum 1 equals angular momentum 2. So that means I1 omega 1 equals I2 omega 2. So angular momentum is the moment of inertia I times the angular velocity omega. And so since there's no torque on the system, then this has to be true. Conservation of angular momentum. Okay, well, what's the initial angular momentum? If the person's standing up in a straight line, then it's kind of like a rod. Let's say the mass is 75 kilograms and the length is 1.75 meters. Now, a person is not a rod, okay? But I don't care. I'm going to do it anyway. So if you look up in a table, you could say I1 is going to be 1/12 ml squared. That's the moment of inertia of a rod when it's rotated about the center. So I know L, I know M, I can calculate that. So that goes right here. What about I2? I2, the person's like this. So that's kind of, I don't know what you would say here. Let's say this. Let's say that this I is going to be, I2 is going to be equal to 2, it's like 2 rods. It's like this. And so this is going to be L over 2, L over 2. So I have 2 half-length rods rotating about their center. So it's going to be 1/12 m over 2 times L over 2 squared plus 1/12 m over 2 L over 2 squared. So now I have two rods together. Okay, and this is just my approximation. So of course I can add these two terms together and I get 1/6 m over 2 L over 2 squared. So that's 1/12, but then I square this and I get a 4th. So I get 1, so 12 times 4 is 48. 12, yeah, I think that's 48. 12, 40, yeah, it's 48. So it's 1 over 48 m L squared. That's I2. Approximation, people, it's just an approximation. Okay, so now I can get an expression for omega 2. Omega 2 equals I1 omega 1 divided by I2. So this is going to be 1/12 m L squared omega 1 over 1/48 m L squared. And of course, that's actually really nice. Those two things cancel, and I get 48 over 12 omega 1, which is equal to 4 omega 1. So it's going to be rotating 4 times as much. So I know that final speed. Okay, so I'm doing pretty good now. I have delta t, and I have omega 2. And so I want to know how many rotations. So let's just say omega 2, if it's constant rotation rate, angular velocity, is going to be the change in angular position over the change in time. That's the definition of angular velocity. If I solve that for delta theta, I get omega 2 delta t, and that will give me the how many radians a person goes through. And then I can convert that to revolution. So we got it. So let's do it. So let's put everything in. Delta theta is going to be omega 2, which is this, 48 over 12 omega 1 delta t. Omega 1 is 2 pi. I had that, 2 pi. So let's put that over there. Omega 1 is 2 pi. And then I can put in delta t, so I get 48 over 12 times 2 pi radians per second times delta t, which is this. So it's going to be the square root of 2 times 10 meters divided by 9.8. And that's going to give me my angle that I rotate through in radians. So let's just put that in my calculator. Don't put it in your calculator. I'm doing my calculator. So I'm going to do this first. 48 enter. Oh, I did that already. Where'd I get? Oh, this is 4. I don't know why I put 48. Okay. So let's do 4 times 2 times pi. So 8 pi. 8 enter pi. Turn that into a number times. And then I need to do this 20. 9.8 divided by. Take the square root. And that gives me 1.42 seconds, just so you know. So that does seem realistic. I mean, that's actually kind of long, but it's 10 meters, right? You got time to think about that. And then I multiply this together, and I get 35.9 radians. Okay, so now if I want to convert that, delta theta is 35.9 radians. I can say there is one rotation is equal to 2 pi radians. So I'm multiplying by the value of 1 here, so I'm not actually changing things. And the radians cancel. And yes, I'm actually undoing what I did. But let me just do it anyway. So 2 divided by pi number divided by. And I get 5.71 rotations. So let's say 5. The answer is 5. According to mine, and I'm going to go Google it, but I don't have my Google right with me. But I wonder what the record is. I would guess it's something higher than that. I would say it's probably closer to 7 or maybe even as high as 10. My estimate here is probably fairly low for the moment of inertia of a Tucker. Okay, but there you go. Flips on the high dive.